All right. Welcome to United Astronomy Clubs of New Jersey. So, while we're waiting for people to wander on down and find a seat, uh, thank you for joining us. We would love for you to check out our website, uacnj.org. It's where you're going to find things like what our upcoming talks, our past talks, and links to those on our archive in YouTube, as well as links to all our member clubs because we are a club made up of other clubs. Uh, it appears that one of our volunteer observers is enthralling the crowd. So I don't know if you could hear it, but we have one of our other observers like, hey, bring the people down here. Uh, so in addition to our website where you can check all those things out and our member clubs, because the best way to get involved in astronomy is to find the club that's closest to you, because they're going to know all those tips and tricks that we in a different area might not know. In addition, you can check us out on our social media pages, our Facebook, our Instagram, as well as our Discord, because that is a great place to get your questions answered. Also, sharing your astronomy endeavors and your astrophotography. In addition, we also have a online merch store. So if you want some sweet, sweet swag delivered direct to your door, store.uacnj.org is where you can find that. We do live stream these on Twitch as well as YouTube. So if you're here and you ever can't make it here or thought, man, I wish I could go see that talk, you could join us in chat and say hi. All right, so I'm just going to let people kind of get settled down here. I see a number of people, some of whom just drove in and got parked, so they've been running to catch up. All right. So, for everyone here, welcome to United Astronomy Clubs of New Jersey. Couple safety briefings. If you need to use the bathroom, that is the porta potty in the back, illuminated by the red light. After the talk, I'll be available in the little museum area and gift shop area that we have, in the door outlined by red, also to your right, my left. But unfortunately, I can't be in two places at once, so until after the talk, I'll be out here helping you guys. When we go to leave, we are using our headlights because it'll be dark, and we don't like running people over, and I'm sure you do not want to get run over. That being said, if we are wandering around with flashlights, do keep those flashlights and other lights pointed towards the ground if possible, just because we don't need to unnecessarily blind people with flashlights and lasers. Okay, so tonight's talk is Bang Woosh Zoom with Paul Fischer. Paul has a Bachelor in Engineering and Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though always interested in celestial objects, Paul's official start in amateur astronomy was one night several years ago, lying in awkward positions on his roof in the freezing cold. Kind of like tonight, honestly. It's a little bit breezy and cool. Holding a pair of binoculars, catching a brief, clear glimpse of the Galilean moons of Jupiter. After some introductory reading, which I'm sure his introductory reading is like my height, whereas my introductory reading is maybe this folder. What? I know you're a bookworm.
A little bit.
Uh, he purchased his first telescope and is now an active member of both Northwest Jersey Amateur Astronomers, which is one of our member clubs, and he now volunteers here at UACNJ as well. With that, here's Paul.
Thanks, Kim. Hello, everyone. I'm Paul, and my presentation tonight is Bang Woosh Zoom. What do you think we're talking about? That's a good guess. That's not what we're talking about. What? Of everything? Of everything, yes, it's the origins of everything. It is the Big Bang we are talking about tonight. All right, the Big Bang Theory. It's a slightly irreverent book report on the first 3 minutes. So the first 3 minutes is an excellent book on the subject. Just a warning here. Well, for any correct information, let's get this stuff started. Steven Weinberg, the first 3 minutes, A Modern View of the Origin of the Universe, updated edition. Anything that is good and good information came from that book. For any mistakes, you can blame me. I'm the one who messed up. If you detect anything that you think doesn't ring true, that's all my fault and not Dr. Weinberg's. What are we going to cover tonight? We're going to talk a little bit about the author, a quick review about some science concepts, expansion and redshift, cosmic microwave background, a few select moments in times, and then we'll go into some afterthoughts. But first of all, I want everyone, when you're listening to this, the science gets a little thick and heavy. We talk a little bit about particle physics. We talk a little bit about the Hubble constant. We talk a little bit about some major concepts in science. And don't worry, the argument for why the Big Bang is the Big Bang and why we believe that is how the universe started is actually relatively simple. So don't let the thick science get in the way of the simple argument. Okay, so you can always try to understand the thick science offline a little bit more, look it up, get comfortable with it. But what I want you to leave today with today is the simple argument. All right, a little bit about Steven Weinberg. He was born in 33, and he left us not too long ago, 2021. This is him there, and you notice that every photographer ever has pictured a physicist with equations on him behind the board, because that's just how they live. A little bit of a trope, but there he is. Here he is, pictured with other Nobel laureates, with Queen Beatrix. And Queen Beatrix of the Netherlands. Queen Beatrix is no longer the queen. I think she abdicated. I think her son is king now. A very abbreviated list of Dr. Weinberg's professional achievements. And he's obviously a very storied and impressive individual based on these. He's got his bachelor's from Cornell in 1954, a PhD in physics from Princeton in 57. He did contribute, not only contributed, but he authored original research and theories in particle physics and in physical cosmology. He shared the Nobel Prize in Physics with Sheldon Glashow and Abdus Salam, and I apologize for any mispronunciation of names there, in 1979. Numerous other awards in the sciences and for science advocacy. He was a researcher, faculty, or lecturer at Columbia, Berkeley, MIT, Harvard, and the University of Texas at Austin. He wrote 15 books on science, science communication, and science philosophy, and he had multiple scholarly and popular articles. So, an expert. So we can maybe all agree on that. So, yay, let's review some science concepts. We're going to need these to remember these when we talk about the Big Bang. Almost no equations, 100% guaranteed, or the money you paid to get in here tonight will be refunded to you. All right, we're going to talk a little bit about particles. So this is like a steam chamber or some other imaging device for particles. And this, of course, is a particle accelerator. About particles. Particles that move fast enough when they collide will overcome intranuclear forces and are annihilated. New particles are then created from the resulting energy. I want everyone, so maybe when, I certainly had the concept, but maybe when in a particle accelerator and we heard that they're smashing particles together, we thought that what was left over might be, I did anyway, the debris of those particles crashing together. But that's not how it happens. Okay? What happens when those particles crash together is that they completely go to energy. So they are no longer particles. They are nothing except energy. And then they reconstitute into particles afterwards based on the amount of energy used to create the particle. So that's an important concept. It wasn't debris. It's not debris. It's particles come directly from energy. A particle's rest energy is given by E equals mc squared. Oh, that's an easy equation, right? We're familiar with that one. Particles are created in matter-antimatter pairs. So if we have one matter of particle particle created, its antimatter brother or sister is also created at the same time. The photon is a particle with zero mass. It mediates the electromagnetic force, light. Electrons are leptons and are small with small mass. A lepton is a type. Who said that? Okay, very good question. So there is a chart called the Standard Model. If you look that up in Wikipedia, Wikipedia's articles on it are very good. The Standard Model will break down the various types of particles there are, and lepton is a classification of particles. Electrons being one of them. Protons and neutrons are baryons, another type, another classification of particle, made up of quarks. They are larger and more massive than electrons. Neutrinos are also leptons and react with baryonic matter only extremely weakly. Okay, so you might have heard of neutrinos. The real kicker about those is that those guys don't really react too much. You can go through a light year of lead with them quite easily. All right, we remember from physical science. You might remember this way back in 6th grade or maybe in high school, the Young's double slit experiment. We shine light on two slits. And we get, instead of getting two lines on the wall behind the slit, we get a pattern of waves. And therefore we discovered the dual nature of light, that it is both a wave and a particle. Okay, so Young's double slit experiment, we figured out that these weird, very tiny things actually are weirder than we thought, that they have a dual nature to them. And about light, we are talking about spectrum here. So here is a spectrum. This is the rainbow, basically. It's light shown through a prism. And different frequencies of light travel through the prism differently, and we spread out the light into this rainbow. We're familiar with rainbows. That's all that's happening, is that we're making this rainbow. However, in black bodies, what we end up seeing are these absorption lines. And what's happening there is that something gets in front, like gas or something in space or something in the lab, gets in front of that light coming to us. and that light is absorbed by that something and then redirected because it shines out from that something again, but it goes off instead of straight to your eye like the rest of the light was traveling, it might go off in a random direction. Okay? So what happens there is that the light in those where it hits those things and it shines in a different direction, we get dark lines called absorption lines. So that's all that's happening. And just so we remember, redshift is, if you notice that it's the same, if these lines, we can call it, I don't know what this particular spectra is, unfortunately. I guess I should have looked that up. No, I didn't write it down. However, whatever it is, we'll call it X. X, you can see that this is still X because the pattern is the same. The lines correspond to each other, but this one is a little bit to the right, isn't it? And that's just called a redshift. It shifted to the red, to the right, red, and therefore it's called a red shift. Same stuff, but shifted to the right. That's what a red shift is. All right. Light can behave both like particles and waves. I had said that previously. Light from objects in space can be collected and analyzed. Their spectra and apparent luminosities can be directly measured. We have very sensitive instruments that can measure all that stuff. Similar to sound waves, light is subject to the Doppler effect from relative motion. So we go back here and we see redshift, and that is the Doppler effect for light. When the train goes as it goes by, that's what it looks like for light. Instead of hearing it, we see it in a redshift. Redshifted light is lower frequency, longer wavelength from objects moving away from the observer, and is less energetic. It's cooler. The light is cooler because the light's going that way away from us, or that way away from us, or that way, whichever way it's going, it's just going away from us. Blue shifted light is higher frequency, shorter wavelength from objects moving towards us. And visible light is a small piece of the entire electromagnetic spectrum. They include gamma rays on one end, radio waves on another. The fastest anything, including light, can travel through space is in a vacuum is the speed of light, which is c equals almost 300, let's see, that's 300 million meters per second, or approximately 671 million miles per hour. Pretty fast, but not infinitely fast. Expansion and redshift, the expansion of the universe. This is the first part of the argument for the Big Bang. Expansion and redshift. What are these, everybody? I took these pictures up here, by the way, UACNJ. I took these pictures here. What are those things? Galaxies. Those are galaxies. New improved bonus material. I was proud of this one. A couple of years ago, we had an M101. You see this picture and this picture. These are the same galaxies. This one's rotated a little bit, but it's this arm here and this arm here. They're the same arm. You see this bright spot in the galaxy that is here but not here? Supernova in M101. Kind of cool, right? We didn't always know what galaxies were, though, did we? We know those now. We know what they look like. We thought that maybe they were gas clouds. We saw them previously. When I say we, I mean the human race. But we didn't know what they were. We didn't even know the sun was the center of the solar system, and so we had a long road to try to understand this stuff. However, in 1750, Thomas Wright proposed the Milky Way was a flat slab of stars in which our solar system resides. In 1775, Immanuel Kant proposed that some nebulae are that astronomers observed, that those gas clouds I was referring to, are actually circular disks like the Milky Way is. Though widely accepted, Kant's ideas of a universe full of galaxies was debated for the next 150 years. We could not prove it. And scientists like proving things, right? We can't just say that's how it is because we think it that way. We actually have to have data to back that up, right? As again, I'm using the we as the human race, all of scientists. In 1923, Edwin Hubble observed the first Cepheid variable stars in Andromeda, and using previous work from Henrietta Swan Leavitt and Harlow Shapley, proved that Andromeda was its own separate galaxy and not a nebula in our Milky Way. What they were able to do with this Cepheid variable is that if one remembers physics and degrees of freedom and things like that, if you have two equations or two unknowns, you need to have two equations, right? And what this Cepheid variable does is give us another equation so we can, excuse me, now solve for the two variables of brightness and distance. And so we were able to figure out how far away Andromeda was, and it was really far. 200 million, 2 million, 2 million light years away, something like that. Hubble's originate estimate, approximately 1 million light years away. Modern estimate is 2 million light years away. Okay, so that's what Hubble did for us. We proved that galaxies are their own thing separate from the Milky Way. So what does that mean? Astronomers, in the meantime, after Kant made all his theory or proposed that galaxies were their own separate things further away in space, astronomers weren't sitting around waiting for Hubble to make his proof, right? What they were doing is, since the mid-19th century, and amongst many other things astronomers were measuring the spectral shifts of, they were measuring those galaxies, and they found here that they noticed that with only a few exceptions, all galaxies were redshifted. And if we remember from the science review, redshifted means it's doing what? It's moving away from us. So all of the universe is moving away from us. Hubble announced in 1929 that he discovered that the redshifts of galaxies in all observed directions increase roughly in proportion to their distance from us. This became known as Hubble's law, and its accepted current thought on the value of Hubble's constant is between 67 and 77 kilometers per second per megaparsec. What does that mean? It means the further you go away from us, the faster everything is moving away from us. However, I want you to be careful. That sounds a lot like we're the center of the universe, right? However, that's not true. Because no matter where you go in the universe, the further away you go from that point, the faster everything is moving away from you. So think about it this way. If I were to, can I have a volunteer here? Come on, man. Thank you for being brave. All right, you have to stand in the white box, otherwise we don't see on camera. All right, so I want you to grab an imaginary sheet, and this sheet's made of rubber. Okay, now we're going to step back from each other and step back one more time. And if we were to step back infinitely from each other, that's what's happening to the universe. So each point on that sheet is moving away from each other. Now, if that sheet is infinitely large, thank you very much for allowing me to use you as a prop this evening. So So if you imagine that sheet is infinitely large, there is no center, and every point on that sheet is moving away from each other, and that's what's happening. Here's Hubble's law. I think this was actually Hubble's original plot as presented. The universe is not static. It is currently expanding and continuing to expand. The universe is homogeneous and isotropic. This is the cosmological principle. That means it's the same anywhere you look, in any direction. And we can now play with the universe's time coordinate in our minds. So we know that since everything's moving away from us, in the future it's going to be more distant. But then we have to then we can think backwards. If everything is going to be further from us, then that means back in time everything was closer. Okay? So now you're getting to this simple argument. Point one is that you can now play with the universe's time coordinate in our minds, fast forward to predict its fate, rewind it to create its origin. So the more you turn it back, the closer things were to each other. And you can take that to an extreme. In other words, a singularity. Dr. Weinberg introduced Friedman's critical density and wrote some about the universe's fate. If you hit the rewind button hard enough and long enough, almost all the way back to the beginning of time, you can see that how things must have been a lot closer together than they are now. How close? The implication's implication. I mean, not just a lot closer, but a lot closer. You're not quite getting it yet. Really, 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 really close. Not normal close, weirdly close. Particle physics close. And from an infinitesimal and hypothetical point before particle physics close is when maybe it all started. We now call this theory the Big Bang. And now, and you've heard like that when we are colliding particles together in particle colliders, that we are exploring the origins of the universe. But now you know why particle physics is a very important part of our theory of the Big Bang. Because at one point in time, if you rewind that clock all the way back to the beginning, everything was so close together that it was particle physics that was ruling what was happening in the universe. Things are so close that there was just no room in between them. There are many theories about what existed before. However, we don't have any physics for what actually is happening in a black hole or before things made sense from a particle physicist's point of view. So we have to stop it right before the Big Bang, right after the Big Bang happened. Okay, we can say that things happened, and that's why we're going for more and more powerful collisions, because we can go that much further back in time and understand those higher energy states. However, we can't go all the way back to when it was possibly a singularity. It may never have been a singularity. It could be. We don't know. We can only go back as far as we have the energy to make particles collide together here on Earth right now. Because again, scientists like data. They don't like just making suppositions. They could say it might have been a singularity, but they'll say might, and they'll never tell you that that's how it was. Okay, that was argument one. And it was a pretty simple argument. We just rewound time, observing what the stuff is doing now, and just rewound time and said, oh, it must have been like this back then. All right, here's the second one. Here's the second point of the argument. Theoretical physicists predicted the CMB, the cosmic microwave background, over 10 years before its discovery. It was postulated from exploring the particle physics of the early universe. However, they did not predict its importance as corroborating evidence of the Big Bang theory. So they had this theory that it must have looked like this, but they didn't think, if we look for it and find it, that might actually prove help prove the theory. They didn't put that together. So experimental verification was not a priority of the cosmic microwave background. They didn't look for it because they said, this cosmic microwave background thing might exist, and then they just left it. I'm sure some people didn't just leave it and they, submitted papers and all that type of stuff, but it never became like a overall priority in the science community. So experimental verification lagged its actual discovery. And then once upon a time in New Jersey, we're close to this one, right? This happened in Homedale, New Jersey. These two gentlemen here. In 1964, Arno Penzias and Robert Wilson worked for Bell Labs in Homedale. They were commissioning a radio telescope for a survey of the Milky Way. They were troubleshooting sources of noise in the signal from the receiving system. They were measuring in the microwave wavelength, so a wavelength of 7 of light, but a wavelength of, this form of light is microwaves, at 7.35 centimeters. They found a stubborn source of noise that didn't depend upon where they pointed the equipment or the time of day. So what does that mean? That means wherever they pointed this big instrument in the sky, it was coming from everywhere, all the time. This signal corresponds to the excitation of electrons in a closed thermal system at a temperature of 3.5 Kelvin. This is referred to as a black body temperature. A lot of science in there, right? All that you need to take out of that is that's a specific wavelength of light. And it might refer to a heat. Though colleagues Penzias and Wilson, Penzias and Wilson were put in contact with physicists of Princeton who had theories about leftover radiation from the early universe, and who were setting up their own experiments at that time, not prior, but at the same time. Peebles, Dick, Roll, and Wilkinson. Penzias and Wilson had found this theorized leftover radiation. They won the 1978 Nobel Prize for Physics for their discovery. Their discovery was a complete accident, but they found this theoretical leftover radiation from the Big Bang. We'll go into a little bit how this radiation came about. But so physicists predicted it separately. Somebody else found it. And now, so they weren't even say, oh, we have this theory and now we found it. So somebody else found it. So it was complete happenstance that wow, we actually did find this theoretical leftover radiation. So therefore, it's not like they were like, oh, we mislabeled this because we think this is the thing that we thought it was. No, somebody else completely different found it. So gives a little bit more oomph to the story, doesn't it? Because somebody else found it. It wasn't any manipulation of data. It was just things that happened. After the Big Bang, but what is the CMB? So what is the cosmic microwave background? After the Big Bang, the expanding universe was very hot, very dense, soup of radiation and elementary particles. Matter did not exist the way we think of it now. Even though the universe was expanding rapidly, the mean free time between radiation and particle interactions was unimaginably fast. You don't have to worry too much about what that means. All you need to know is that radiation couldn't go anywhere. The universe was opaque. Light could not leave this stuff. It was trapped. The radiation and particles were in thermal equilibrium and behaved like a black body. More science. That's all right. The universe cooled in thermal equilibrium until it reached around 3,000 Kelvin. Then electrons bound to atomic nuclei and regular matter formed. The stuff we see today, the universe eventually cooled into the stuff that we are standing on, that we're made of, that is all around us. The universe's density dropped and became transparent. The radiation was released, and that is the important part. The light and energy was trapped. The universe cooled enough because after it expanded, and light was let go. The universe continued to expand. The wavelength of the light expanded with the rest of the universe. It is redshifted. Remember, it got redder and redder, cooler and cooler. Remember, we said that in the, when we reviewed what light does. And that black body radiation is now what we see at 2.725 degrees Kelvin, just as predicted, all around us, everywhere in the universe. That's what the CMB is, and that's corroborating evidence for the Big Bang Theory. That light that got released, we can still see it right now. At the temperature we expect it to be, because it cooled and expanded. Black body, this is a let's see if I wrote down Planck distribution. This is a Planck distribution showing radiation of a black body. And look, right here, right around here, 3 centimeters wavelength. Here's an actual picture of the cosmic microwave background. You may have heard the cosmic microwave background before. You may have seen a picture of it, but hopefully now you have a little better sense of what the cosmic microwave background is. All right, so a lot of the book was, okay, what is, now we went into the theory a little bit. What is the timing of how things happened? And the way he did this is sort of like, I called it a cosmic, a play, and is a few ticks of the cosmic clock. You might, the book, if you remember, was called The First 3 Minutes, so you might figure out how long this play is going to take. All right, lights up. We start somewhere very soon after the Big Bang. The temperature is 100 billion Kelvin. That's a lot of Kelvin. The universe is a soup of matter and radiation, and it is a state of thermal equilibrium. The only matter that exists are the electron, the positron, the neutrinos and antineutrinos, and the photon. If you remember, the positron is the antimatter sibling of the electron. The density of the universe is approximately 3.8 billion times that of liquid water. Pretty dense. Excuse me. About 1/10 of a second later, the temperature is 300 billion degrees Kelvin, 30 billion degrees Kelvin, down from 100 billion. So we're getting there. We're cooling down pretty quick. The universe is a soup of matter and radiation and is in a state of thermal equilibrium. The only matter that exists are still the electron, the positron, neutrinos and antineutrinos, and the photon. Free neutrinos and protons are formed and blasted out of existence. We're starting to form baryonic matter. The ratios differentiate between 38% neutrons and 62% protons, and the density of the universe is approximately 30 million times of liquid water. Happened pretty quickly afterwards. But a lot of stuff happened in between, so maybe weird things related to time were happening at the same time. Tick. The next tick is almost just over a second later, or a second from the Big Bang. The temperature is 10 billion degrees Kelvin. The universe is a soup of matter and radiation, and it is a state of thermal equilibrium. And I want to, this is read on purpose. Just keep in mind, we haven't talked about neutrinos really too much at all, other than mentioning them in the beginning. The universe becomes transparent to neutrinos. Free neutrons and protons are formed and blasted out of existence. The ratios differentiate even more. There's 24% neutrons and 76% protons. The density of the universe is approximately only three. Now, we're no longer millions, we're 380,000 times of liquid water. Almost 14 seconds have elapsed in our play. The temperature is only chilly 3 billion degrees Kelvin. Electrons and positrons are stable at this temperature. They begin to annihilate each other. Neutrinos previously freed are cooler than the rest of the universe. The balance of neutrons to protons is 17% to 83%. And some stable nuclei can now form. Helium and atomic weights above are still suppressed. So we're getting some hydrogen ions forming. 3 minutes now. This is the, this is sort of the end of the, we're getting to the end of the play here. 3 minutes and 2 seconds have elapsed. The temperature is only 1 billion degrees Kelvin. Electrons and positrons are mostly gone. They have annihilated each other largely. Luckily, they didn't all annihilate each other. Otherwise, we wouldn't be standing here right now. Electrons and the universe is now mostly consists of photons, neutrinos, and antineutrinos. The balance of neutrons to protons is 14% to 86%. Some stable nuclei now form. Helium nuclei can form, but are suppressed because deuterium, a necessary precursor to helium, is still suppressed. The energy is still too much for deuterium to form. And if you have ever looked at how suns create helium from hydrogen, deuterium is a necessary step in that reaction. Approximately 3 minutes and 46 seconds have passed. Deuterium nuclei are now stable. Helium nuclei form at a rate twice that of available neutrons in the universe. 13% neutrons to 87 protons. The temperature is now 9 million degrees Kelvin. The next tick is 34 minutes later, and almost 35 minutes later. The temperature is 300 million degrees Kelvin. Electrons and positrons are gone, except for one part in 100 million. Nuclear processes have stopped. Nuclear particles are bound in mostly hydrogen or helium nuclei. Guess what? That's what these ratios dictated. So the particle physics that tell us how much of that stuff was around at different types helps us to see, yeah, that's why we have this much hydrogen in the universe. Because this much stuff, this neutron to proton ratio existed. Nuclear processes have stopped. Nuclear particles are bound in mostly hydrogen or helium nuclei. It is still too hot to form stable atoms, however. In other words, they were ions. The density of the universe is approximately 9% of liquid water. So still dense, because space is mostly vacuum, the way it is now. But it was at this point, 34 minutes after the Big Bang, it was already less dense than water. Not much interesting happens for 700,000 years after those 34 minutes. The temperature drops below 300 degrees Kelvin. Stable atoms are now possible. So it's no longer ions, but actual stable atoms. Free electrons and atomic nuclei begin to pair up and make happy little atoms. The universe becomes transparent to radiation. All right, that's the CMB we were talking about. So about 700,000 years after the Big Bang, the universe became transparent to radiation. Stars and galaxies begin to form because we now have atoms. And another 10 billion years or so go by, and then at that point, Dr. Weinberg writes his book, The First 3 Minutes. So here we are. Afterthoughts, things we want to think about now. The cosmic neutrino background, as predicted. So let me see if I can quickly go all the way back to that first red one. Here we are. The universe becomes transparent to neutrinos. That sounds a lot like the one we talked about in great detail, the cosmic microwave background. So the universe becomes transparent to radiation. That's where we got the CMB. However, there was one before that, right? The universe becomes transparent to neutrinos. Aha! Another thing to test the theory. So if there was a cosmic microwave background, then we must have a cosmic neutrino background, and we have predicted ourselves because we noticed that the similarity there. But I can say that we've also found the cosmic neutrino background, though it's not as popular as most people haven't heard the cosmic neutrino background, but have heard of the cosmic microwave background. This one's cooler, though. You'd expect it to be cooler because the neutrinos left first, and then the radiation left afterwards. So this one's cooler at 1.75 degrees Kelvin. Cosmic inflation and the CMB. There's a point in the expansion of the universe where the space actually expanded faster than the speed of light, and the way that happens is that we can't move faster than the speed of light through space. But there's nothing that says that space itself can't move faster than the speed of light. So that's the physics behind that. Before the Big Bang, as I said before, one theory is that it's a singularity, but we can speculate that maybe it was a singularity, or maybe it always existed as more and more infinitely dense object. However, we don't have any physics to describe that, so we can't really explore that from a scientific perspective. The matter-antimatter asymmetry. Remember, Dr. Weinberg illustrated, and I said that the neutrinos and antineutrinos, the electrons and and the positrons started destroying each other. And luckily, we wound up with electrons that stuck around, because that makes up stable atoms, which makes up us and the rest of everything we see. And so luckily there's an asymmetry there. There wasn't enough anti-particles to destroy the stuff that we are, leftover stuff that we are made up. Most of it was destroyed. The little remaining part, which comprises the whole universe, we're lucky that hung around. We don't know why. So that's more science that needs to happen. Dark matter and dark energy, of course, are a thing that is currently being explored and is a big unknown in science. And the heat death of the universe. So what happened? So we talked about what happened maybe in the beginning. We talked about that everything's going far away from us, further and further away. Well, if you put the time scale out far enough, then everything is away from everything else. and there's a possibility. One theory of how the universe ends is the heat death. Everything's just so far away from each other. Everything is so lax, is so low in energy that nothing just happens perpetually, trillions of years from now. All right, here is a current model. Here is the Big Bang. It happened on this side here, and then the universe expanded. You notice this part here where it expanded very rapidly. You notice it was 0.1 second, 1 second, 30 seconds, 3 minutes. So all that really cool stuff that we were talking about today happened as the universe expanded extremely quickly, very close to the Big Bang. And then it sort of languished for 14 billion years afterwards. All right? Things are still expanding and getting further and further apart as you go by. Just so you know, Dr. Weinberg's book, etc., has been updated the first 3 minutes. However, the current, although the structure of how things happened is basically the same, some of the timings are a little bit different in the modern theory. Not way off in the sense that it completely changes the science, but some of the timings are a little bit different nowadays. Didn't the you might have heard from some news articles? Didn't the JWST break the Big Bang theory? No, it didn't. There were early identification of some anomalous results relating to the size of early galaxies, which scientists love because they say, hey, maybe there's new science going on here. However, the size of the early galaxies were originally estimated were incorrect. The mistake had something to do with light extinction. So if you're familiar at all with things in space, gas or something can get in between. In fact, it's a big universe. There probably is something between us and a star or a galaxy that we look at in the sky, and scientists calculate how much light gets scattered when it passes through that thing. So the scientists have to take in this extinction, and sometimes that extinction can be calculated incorrectly, and therefore the distance might be off. Current estimates of the galaxy's sizes fit the CDM model of galaxy formation to help combat motivated reasoning. And the reason I say this is that some people are very happy to tell you that the JWST broke the Big Bang Theory, and that's because they want to prove the Big Bang Theory wrong. So to help combat motivated reasoning for these people that ignore the science to try to prove it wrong, there is a by Harry Frankfurt, who is a philosopher. There's a small pamphlet or a small book on bull stuff, he calls it, and The Skeptic's Guide to the Universe with Dr. Stephen Novella and others, and to get an idea why some people might categorize some of the science. I just want to thank everybody for listening to the Big Bang Theory, and urge you to join an astronomy club, and stay safe, everyone. And unfortunately, it's cloudy, but do what you can to enjoy this evening. Thank you for listening.
All right, so we are going to have a Q&A session because, as promised, you probably have questions. We might have answers. If you hear too long of a pause or see us get out our phone and start scrolling furiously, we actually don't know. You should also do research and also always fact check us, because occasionally we get something wrong, because the science we learned as younger people or might not be the science that is actually occurring today. So before I get into questions and answers, I saw a couple of you sneak in after the safety briefing. So, safety briefing. We are using headlights when we leave. We don't want to get run over. We don't want to see anyone get run over. I don't want to fill out paperwork. We're good on that? Any flashlights we might have or whatnot, do keep those pointed towards the ground because we don't need to be attempting to purposely burn people's retinas out. It is dark, it is cloudy and it's dark because it is cloudy. So just be safe when we're moving to our cars. If you need to use the restroom, that is the porta potty in back, illuminated by red. And we also have a museum and gift shop area that I'll be behind the gift shop counter after the questions and answers. All right, so question and answer session for people here. You're going to raise your hand and kind of wave it about. For online people, you just get to type. You get the much simpler form of it. And our first online question is, are you guys going to be able to see the aurora?
I don't think so. It is very cloudy here. In fact, it's supposed to rain later tonight, so I don't think conditions are going to improve where we can. We can see a little bit of redness over towards the east there.
But that's
but
light
that-
pollution
but
from
that-
New York
that's
City.
light pollution from New York City and Hackettstown. So I don't think that's aurora. North to anyone here is over the building that way. So look that way if you happen to see a hole in the cloud. But I don't think we will be lucky tonight. But never say never.
Also, we've kind of been keeping an eye on not only the cloud forecast, but the KP index. I don't know what KP stands for. Someone please look it up because I always forget. Eventually, I will remember. But that index has to be at 8 or 9 to really see it naked eye here. And I think we're only getting up to maybe a 5. And at a 5, even really nice cameras struggle to see that.
KP doesn't stand for anything.
KP doesn't stand for anything, which is why I can never remember it. The more I learn something every day. So was there a question out here? Bueller? I don't even hear crickets. They're all hiding. Like, nope, coming out.
Wave your hand about if you have your hand up because we're looking through light to see you in the dark.
Yeah, I've also been staring at a screen moderating online chat, so I'm completely night blind. So, because I see no waving hands, the next question is actually a comment that you'll get a kick out of this, Paul. When you were asking, what are these? And you said galaxies. Someone said, those are conglomerated space debris. Not wrong.
A lot of it, a galaxy's worth of space debris if one wants to categorize the planets and the stars and everything that make up a galaxy as debris.
Right. So the actual question is, why do galaxies have a number of different shapes? Why isn't it all like, yep, that's a galaxy?
Well, they are themselves subject to formation forces, but also forces from the local groups that they happen to be in, etc. So when you and their own gravity and what they're made up of. So when you get dragging forces and other types of forces, you could wind up with a flat spiral type of galaxy or an 3D elliptical galaxy. Anything that is undisturbed and spinning tends to flatten out in space without friction, tends to flatten out over time as various random forces cancel each other out, and the bulk motion of the not particles but the various elements of that system as the major direction of spin takes precedence, and it'll tend to flatten over time, which is why we have many flat galaxies, flat solar systems, and things like that in space. However, they can be disturbed, they can be subject, like I said, to their own internal forces, and then we have elliptical galaxies and all other types of shapes. So different things happen to different galaxies, and we wind up with a whole bunch of different shapes.
And if you want to see it happen in real time, if you find one of the old playgrounds that has that spinny turntable that flings kids off into oblivion. Um, all the kids start standing up and sitting down, and gradually the only few left are laying down, holding on for dear life before they get yeeted off.
There's probably better experiments than flinging kids off into space, but yes, that is, it's subject to those centrifugal forces.
All right. What's there question out here? All right. So our next online question is, why did the distance go up so dramatically? Is I think this is the 1 million versus 2 million distance. Is it just moving away, or is it just a more accurate measurements are being taken?
I would say it's more accurate measurements over time. Plus, if you think about it, as we base all our measurements off of other measurements in the sky. So if we update one pivotal measurement in the sky, now we have to go and back and recalculate everything, right? So it is definitely iterative. Astrometrics is definitely iterative process. So as we learn more, as we understand more about Cepheid variables, as we measure it using various different methods, etc., we refine our estimates over time.
All right. Do we know where the center of the universe is?
And if you I tried to allude that with the stretching sheet of rubber analogy that one of our live audience members helped me with. So there is the concept that there is some sort of center of the universe is not really, because this is an infinite, as far as we know, we have what we call the observable universe. But we don't know that there is an end, so it's quite possible that it's infinite. That it just wouldn't make any sense that there actually be a center point to something that is infinite. And also, additionally, it doesn't matter, because everywhere we look and every place in the universe, everything is expanding away from that point. So it's not really a location in space. It's just happening everywhere.
All right. So online people do start getting those last minute questions in. I like to give them a heads up because stream delay is a thing. By the time they're hearing that question, we've already moved past the next question. Was there any question out here? I like to also check with you guys, because I'm going through the questions rather fast. All right, so the next is, how do we know the universe is homogeneous? How do we know it isn't something like a failed banana bread where here's a chunk of banana, over there's all the nuts, oh, here's a pocket of dry ingredients here?
We know our observations, and from what we observe, we have observed that it is isometric and homogeneous. However, does that mean that there isn't anomalies? There used to be something called the Great Anomaly, which that through the galaxy on the other side, we're looking through a soup of material in our own galaxy when we look in this particular location, so does that mean that there isn't parts of the universe that are maybe clumpier than others? It's possible. But what we've observed of it so far, it is a denser cluster of galaxies. However, it's not different from any other parts of the galaxy. I mean, the universe. It's so that you know what our observations continue to indicate that it's homogeneous and isotropic. However, if something comes to light in the future, then we will have to accept that reality and try to understand it better to fit into our understanding of the universe.
All right, so the last online question that I see for tonight is, would the universe cooling down slower or faster have affected the end result of the universe?
Uh, I, the end result of the universe. Uh, I think possibly in the sense that some of our cooling values, what temperatures things have wound up, like the cosmic microwave background would be, it would change that, yes. But the fact that it is cooling over time, we would eventually wind up in the same place. So I don't think that necessarily it would change dramatically. However, certainly the values that we are the values of things that we've measured would have changed and would be different now than if they originally started differently. So yeah, I think some things would have changed numerically, but not necessarily the complete end result. Bless you.
Oh, now you said that too early. Now it's stuck. Uh, okay. So, any last minute questions out here? Oh, perfect.
Have you ever seen any UFO around here when you were watching?
Any UFOs? We see a lot of cool things. Of course, a UFO is itself identified as an unidentified flying object. So we see things that we don't know what they are all the time. However, a lot of things that people think are UFOs, we know what they are. Uh, the some of the satellite trains we see, which are very cool to look at, are very. Everyone looks at them and what is that? No, we know that
Starlink.
Starlink. We know that's a Starlink train. That we get calls here all the time from people asking, "What's that bright light I see in the sky?" That's
Venus.
Venus or Jupiter. So
Mars is not following you and gonna pick your pockets in a back alley.
but that doesn't mean that there aren't unexplained objects in the sky. We are constantly finding things in space all the time that we haven't seen before. So that, but what you might be asking about is alien life and things like that. How we don't have evidence of any visitors from outer space coming to Earth. However, we are, I think, as a society, we pretty much have accepted the fact that, and the science seems to support it, that there is alien life. Whether it's intelligent life or not, we don't know. And because the number of planets that are around the huge number of stars there's probably life out there. Whether or not it's intelligent is another question, and whether or not we could ever communicate, because the distances involved require many millions or billions of years for communication to happen back and forth between the two places. So those are all big questions, and we are currently working at finding life out in the universe somewhere. So it's a very valid question. Keep your eye on the news. Hopefully someday we will discover life elsewhere in the universe, and maybe someday we will discover intelligent life somewhere else.
And usually when I go, "What is that?" I get told, "Put your glasses on, Kim." I need distance glasses, but I can't have them on and look at the screen. That's why everyone here is just like a vague humanoid dark shape figure in the night, which is a little scary if you don't know what you're looking at. And then you realize, no, those are people. Those are not the void figures coming to get you. Hey. So I want to thank everyone who's here. Also, everyone who has joined us online on our Twitch and YouTube for the live stream. Thank you all. Do visit us on our social media, Facebook, Instagram. We have our Discord page. Our website is a whole host of information you should check out. And with that, have a good night. clear skies, or at least clearer than we're experiencing now, which it started raining, and good seeing to you all.
Thank you, everybody.